So, Anya, do you want me to just kick along?
We might just leave a couple of people come on, Leif. So once we get critical mass, we might start at a minute or two past the hour, if that's okay.
That works perfectly for me. Just let me know I'm here.
Brilliant. So good morning, everyone. Thank you for joining. As you may have just heard, we're going to leave it a minute or two, leave some people get off meetings, come back from getting coffees, and we will get started. So, hello everyone, welcome to today's webinar. My own name is Anya Long and I work in the NGINX business unit within F5. Today's webinar is on NGINX 101, so it's managing your SSL and TLS configurations. Today's presenter is Leif Beaton. He is one of our senior solutions engineers within NGINX and F5. Leif is going to take you through the webinar. If you have any questions, please put them into the Q&A box at the bottom right-hand corner of the screen, and we will get those answered at the end. Please note that a recording of this webinar will be available afterwards, as will the slides. But for now, I would like to hand you over to Leif.
Well, thank you so much, Anya. Welcome to you all. Thank you so much for spending an hour with us today. I'm sure you're just as busy, if not even more so than we are. So thank you so much for that. What we're going to do is we're going to go through a presentation first and foremost, talking obviously about NGINX and TLS, or SSL as we all commonly call it. And we're hopefully also going to have time to do a quick little demo towards the end, as it were. Now, with that in mind, I think we should just push along because we have a fair amount of content to go through today. So yeah, my name is Leif Beaton. I'm the Global Channel Technical Lead for NGINX for F5, or rather for modern apps as we call it. I'm going to take you through the technical parts of the management of SSL or TLS with NGINX. First, we're going to go over SSL, TLS, and how it works at a fairly high level. We're not going to go deeply into the mathematics of elliptical curves and so on and so forth, so don't worry too much if that's your fear this morning. We're also going to cover the essentials of what you need to understand when you're configuring up your NGINX server to serve encrypted traffic. And we'll also, of course, demo a simple NGINX configuration using a self-signed certificate and talk a little bit about how, if in any way, it differs from the process of using a not self-signed certificate. We can also look at redirecting traffic from port 80 to 443, so that's covered automatically from a user perspective. So first, just a quick word about NGINX. As I'm sure most of you know, that we power a vast amount of the traffic of the internet. Our open source footprint is well in excess of 440 million websites, and I should add, and counting. We cover in excess of 70% of the 10,000 busiest websites, which is it's almost an incomprehensible metric. So pretty much everybody in the industry has heard about NGINX from an open source perspective. been around for 2 decades. It's been gradually taking over the internet, and we're powering the vast majority of it as it stands. This is, of course, a bittersweet week for us in NGINX with the Igor deciding to retire, as it were, but we give him our thanks, and it's really heartwarming to see all of the outpouring of love on the internet for him. He, of course, went on after NGINX open source to extend that into the commercial product that became NGINX Plus, based on NGINX open source, and it extends it by adding an enterprise set of features on top of it, making it a much more suitable solution for the enterprise side of the industry. We have a number of other open source projects as well as commercial products. I'm not going to spend a lot of time talking about them because we have very little time for all the content today, but rest assured you'll find information about each and every one of them on NGINX Plus as well as nginx.org. Sorry, NGINX Plus, listen to me, nginx.com and nginx.org. So a quick overview of TLS or SSL. First, I want to cover a point that might be a bit confusing. Is there a difference between HTTPS, SSL, and TLS? Well, yeah, I suppose, but we use the term somewhat interchangeably. HTTPS, of course, simply means that we're referring to the hypertext transport protocol secure, and the S being the secure component, which means that the traffic is to be encrypted. When it comes to SSL and TLS, the waters get a little bit more muddy because they are distinct terms, meaning distinctly different things, but we kind of use them interchangeably today. The reason for which is probably mainly the fact that SSL in and of itself is deprecated and essentially broken. But today we use it as a term, a blanket term that covers TLS. TLS is a more modern standard built on the legacy of SSL. And TLS is what we would be using today. In fact, we wouldn't be using TLS 1.1. It itself has been considered deprecated for some time now. Rather, we would be using TLS 1.2 and even more preferably 1.3. Why not just use TLS 1.3, the most modern standard that's accepted today for everything? Well, security is always a battle between usability and security, right? So some legacy concerns might dictate that you have to use TLS 1.2, or for that matter, even go as far as 1.1. But what we're talking about here essentially is encrypting web traffic. That's the ultimate end goal of our conversation today. So to take a bird's eye perspective to this, let's start with the end in mind. What we're trying to achieve is communicate between the client, which can be like a web browser, a mobile application, a secure device, and making sure that the client is communicating with whom it believes itself to be communicating with. So we're talking essentially about two things. First is the identity side of it. And to achieve that, we need two things. We need an encryption algorithm, something that can return usable data in a practically unreadable format, so obfuscated through encryption, and a key that can be used with the algorithm to encrypt and decrypt the data. And most importantly, the client and the server need to agree on the key and also the algorithm, so that the client and the server are speaking the same language, so to speak. Now, nearly all of the complicated, computational, expensive parts of TLS has to do with getting to this point. So So in terms of establishing an encrypted connection, how do we get there? Well, first we need to have the basic TCP connection, and that's equally true if the traffic is encrypted or if it's unencrypted. The TCP connection exists in any way, the usual three-way handshake there. But in order for us to speak encrypted, we also need the client to know who the server is. The identity needs to be established, and there needs to be trust. Next, we're talking about the key exchange, and this is, for all intents and purposes, the complicated part. So we want to end up with both the client and the server having the same encryption key. so that the encryption of the bulk of the data is symmetric. The trick is to get that key exchange to happen in a secure way. So, because if anybody else got a hand on their on our key, then essentially it doesn't matter how much we turn the lock; they can simply unlock it, right? So we need that to happen in a secure way. That's the hard part. And ultimately, once we've succeeded at that stage, the bulk of the traffic, any concurrent and subsequent communication can then happen in an encrypted way. So establishing the capabilities and identities is among the first things that we're doing, right? So we need to establish a cipher suite that each of the client and the server understand and support. And optimally, we want to use as complex a cipher as we can. So the list of supported suites needs to be exchanged between the client and the server, and a specific one agreed upon. So the client will supply the server with a list, and equally the server will supply the client with a list. A negotiation happens, and the highest commonly supported cipher will be the result. They agree upon a key, and from there on, the bulk of the traffic can be encrypted. So how does the client know that the server is valid? So if you, for instance, go to your, say, your online bank, for instance, I'm sure you'd want to know that the bank is indeed who they portray themselves to be before you start sending logon details and access numbers for your accounts. So identity needs to be properly established, and that's one of the key components of a certificate, and one of the things we'll be looking at in the demo. So we provide a certificate that will establish the identity, and it's signed, well, not in a self-signed scenario like the one we're going to be looking at later, but a proper certificate will be signed by a trusted authority, what we refer to as a CA or a certificate authority. This trusted certificate authority signs this identity certificate for the server, thereby ensuring that when the server presents this identity certificate to clients, the clients can then trust and also verify, as Reagan said, that the certificate is indeed valid. It can verify its validity by communicating directly with the certificate authority. Hold on. So next in this, we need to ensure the trust. The certificate is sent over from the server to the client. The client can inspect the certificate, and in turn, as I said, communicate with the authority that has signed the certificate and validate each and every component of it. Once that trust has been validated, communication for the key exchange can happen in a secure way, and after which the bulk of the traffic can be encrypted using public values that's mixed with random secrets to create our intermediate encryption on each side. Yeah, okay. So we exchange those intermediates. The color coding here is indicating that we had one communal color to start with. Then we mixed our own colors as our personal secrets and ended up mixing that with the communal color to get a new value. Decrypting the color that we sent from the client to the server, and the server in turn sent from to the client, means that so long as we know what the original secret was, our communal color, we can figure out what their muxed secret was, thereby establishing the key and talking across an encrypted channel for the bulk of the communication. Okay, yeah, so essentially we have a funny little cat and we want to keep our cat a secret. Now that we have established the communication protocol for encrypted communication, we are going to send our cat in a secure way, in a secret and undetectable way to the client. It will be muxed up with the encryption algorithm. It will be transported across the wire to the client, who in turn, after we've negotiated our keys, can decrypt the package at its end, and lo and behold, our cat is secure, happy, and identical on the client side. So hold on a second there. So we're finally going to get to the protocol, right? So all of this is, of course, based on top of bog standard and very tried and tested protocols like TCP, as we talked about earlier. So the protocol, of course, controls the communication between the client and the server. It negotiates the keys, it gets the certificates and encrypts the data. And as we talked about earlier, we absolutely should be looking at TLS 1.2 or above. TLS 1.3 is the newest one, but it's still old enough to have a significant support now around the block. I mean, one of the ones that are slowest to introduce new standards for its own very good reasons would be Red Hat, and they have support for 1.3 in their latest 4 versions, I think. So I think it's safe to say that 1.3 is fairly globally supported at this point. So why use TLS 1.3 then? Well, it's the newest one, and by extension you can kind of read into it that it is the safest one. That would be the hope, but not only that, it's also faster. So it's safer because it eliminates insecure key ciphers. We're going to look at that momentarily. It mandates forward secrecy, and we're going to discuss that briefly during the demo when it comes to Diffie-Hellman and computational groups and so on and so forth. And it mandates bulk encryption. It's also faster. It reduces the handshakes in TLS signups. There's 0 round-trip connections for the session resumption. There's a simpler list of suites. It's essentially, it can boil down to a single suite if we wanted to, whereas TLS 1.2, you'd have a significantly extensive list to communicate between the client and the server for negotiation. What suite are we actually going to end up with? 63% of servers measured today prefer TLS 1.3, and that's very good news for all of us. So as we've seen, critical to security of our connection is the SSL certificate. Even as key exchange protocols has evolved, the SSL certificate remains central in verifying the server identity first and foremost, and preserving the message integrity. So let's dig a little bit into that. What's the SSL certificate used for? It's obviously to establish identity through a chain of verifiable trust, going all the way from the server presenting the certificates through a small number of trusted root certificate authorities. There's a fair few of them today, but still a manageable number. And the browsers and applications are configured to trust. When you install a web browser, be that Chrome or Firefox or Edge or whatever the case may be, it ships with a substantial list of trusted certificate authorities. So any certificate your browser comes across that's issued or signed by such a certificate authority is automatically and by extension trusted. Familiar PKI encryption can also be used to sign and encrypt traffic, so each side know that it hasn't been compromised. So here's a simple chain. This is a real-life example of where we're at NGINX.com. So we're using our certificates. It has, however, been signed by an intermediate, which in this case is our CDN provider. We're using Cloudflare for that purpose. And the certificate is in turn signed by Baltimore Cyber Trust. So as long as Baltimore Cyber Trust can be trusted, anybody receiving our certificate knows automatically and automagically that we are indeed who we say we are indeed where we say we are, and the communication can thus be trusted. So that brings us to 3 types of certificates, 3 main types of certificates and what they're typically used for. You can very easily generate a certificate yourself. That's in fact what we're going to be doing in the lab today. There are web portals that facilitates this. There are command line tools like OpenSSL, which is exactly what we're going to be using. But in any event, the self-signed certificate, while it can provide you a tool for encryption, it's not really valid to establish identity. The reason for that is it's not signed nor created by a trusted authority. Anyone and everyone can create a self-signed certificate for whatever common name. So I can use OpenSSL to create an otherwise valid certificate for NGINX.com, for instance, but obviously no one is going to trust that certificate since it's not established either by creation or by signature by a certificate authority. So using a self-signed certificate to protect a website, sure enough, you can encrypt the traffic, but you will get all sorts of errors in the browser, and we're going to see that in practice later on. When you obtain a certificate from a certificate authority, none of the downsides that we talked about earlier exist. It is trusted by default. You won't get browser warnings and so on and so forth. The downside of a CA signed certificate over a self-signed one is simply one of complexity, time, and potentially nominal cost. But essentially, these boils down to dev and test environments for the self-signed certificate, which is where they rule and are excellent, and production environments for the CA signed ones. Now, there is a kind of a halfway point between these two fellas, and that's what we call a self-CA signed. For a business that runs its own internal network with a number of computers and a number of internal services, perhaps there's an intranet, but you want it to be encrypted and so on and so forth, it might be both cheaper and more practical to put up your own certificate authority. And all main vendors have a certificate authority that you can spin up pretty easily in a Linux environment, in a Windows environment, whatever the case may be. It will act exactly like a formal certificate authority would, in terms of you would send a request to it, it would automatically process the request and issue certificates, assuming that it fits with the rules of its policies. These certificates are indistinguishable in format from a formally CA signed one. However, it would not be trusted outside of your own organization. The reason for that is the root certificate for the certificate authority needs to be distributed to any and all clients, be that machines or pieces of software like web browsers, etc., for trusting the root, thereby knowing that the issuer of the certificate that you subsequently will see is in fact trusted. So, obviously, I mean, obtaining a certificate is only half of the equation. Once you have your certificate, we also need to configure up our software, in this case, our web browser or reverse proxy, whichever the case may be, to utilize the certificate and issue it upon request. So we need to configure up our NGINX instance to use it. Now, in a basic NGINX configuration overview, this is about as basic as it gets. We have an HTTP context within which we can have one or more server contexts, which in turn can have one or more location contexts, which isn't shown here, but we'll see them later. The HTTP can also contain 0 or more upstreams, which is essentially load balancing pools, where we can define backend servers, and so on and so forth. The server and upstream groups are typically contained in different files. So essentially the HTTP context is usually defined, or by default defined, in the nginx.conf, which is the basic configuration file of nginx. Within the HTTP context, there would be an include statement that will include any .conf file found in the conf.d subdirectory. So in the conf.d subdirectory is typically where we would put any and all of our individual configuration files. So when it comes to the NGINX SSL configuration, it's pretty straightforward. And as a matter of fact, it's extremely straightforward. All we need to do is provide a pointer and a definition for the SSL certificates or certificate bundle. It can include the intermediates and so on and so forth. And we also need to include a pointer to the SSL certificate key. In this particular example, these are put directly in the file system. There are other alternatives as well. We can can provide them through variables, through the key value store, etc., etc. But for the intents and purposes of our simple demo today, we're just utilizing the file system. We're specifying the SSL protocols, and we're giving it an SSL cipher string that's specifically for TLS 1.2, and we're also providing an SSL configuration command for cipher suites. This is more intended for the TLS 1.3. Yeah, so we've essentially gone through this, but to reiterate, the port to listen to, this is actually vital to highlight. In NGINX, we make no assumptions. So simply saying that we're listening on port 443 does not make any assumption about the encrypted or unencrypted nature of that traffic. In order for that, even if 443 is the default port for HTTPS. So in order for us to specify that this is indeed encrypted traffic we're looking for, we're also using the notation SSL in the listen directive. That way affords you a lot more freedom while still enabling you to achieve any and all other results that you want. The server name obviously is essential to match towards the certificate, because the certificate isn't issued to an IP address. If that was the case, web servers that dynamically change IP addresses would be complicated, not to mention that clustering would also be complicated, because one and the same domain name can point to a cluster of IP addresses supporting requests for those assets. So the name is essentially the common name. We're going to look at that through the certificate creation in the example shortly. Yeah, the certificate and key we've covered, the available protocols we've covered, the cipher string for TLS 1.2 and 1.3. So this is a TLS 1.2 cipher string explained very, very simply from a bird's eye perspective. What it does here is it's specifying some ciphers to use. Like it's going to use high security ones, so only use the high set strength ciphers that's available in a collection. It's also going to exclude sites that don't use authentication, and indeed it's also going to exclude sites that use insecure or weak hashing mechanism. The exclusion is happening by virtue of the exclamation mark in front here. Yeah, so essentially this would be the way to set the cipher string using OpenSSL. So OpenSSL is the tool that we'll be using today, and it's very commonly used across the industry. I'd say it's the de facto standard in the Linux-based world. When it comes to TLS 1.3, the string looks slightly different. It's not conceptually very different. Essentially, what we're doing is we're defining the protocol TLS. We're also defining the bulk encryption mechanism, and ultimately we're also defining the key derivation, which has some implicit meaning as well when it comes to key strength and stuff of that nature. As we mentioned earlier, TLS, historical or legacy versions of TLS typically has a much longer list of cipher suites. But this is not one of them times where more is better. This is one of them times where more is less. TLS 1.3 has a grand total of 5 recommended suites, yet it is vastly superior to the 37 cipher suites available in TLS 1.2. And when you have TLS 1.2 with backwards compatibility, you're looking at a grand total of 319. A bigger number here isn't better. It simply means that it has more broken suites it has to carry with it. So yeah, let's go ahead and do a brief little demo on this subject. Just to give you an overview of the simple environment I've set up. Essentially, I have a client, which is me sitting here, and the end goal, the objective of this this demo is for me to be able to communicate with the NGINX front end, NGINX Plus here, in an encrypted manner. The NGINX frontend essentially functions as a reverse proxy to an NGINX backend, here illustrated by NGINX open source icon. In my particular environment, it is in fact NGINX Plus, but it carries no meaning specifically. And I'm going to do that in an unencrypted way. So encrypted to the front end, unencrypted to the back end. Why is this a very common pattern? Well, it's because the communication between the front end and the back end is typically happening in a secured environment, where we have eliminated the possibility, or at least the probability, of eavesdropping. This communication is happening over the open and unsecured internet, where eavesdropping is happening all the time. It's not even difficult. So we're traveling over an unsecured network, therefore we want to secure the communication. Here we're traveling over a secured network, therefore we're less concerned with the encryption of the traffic. With that in mind, I think I'm going to pop myself over to a terminal real quick. So in my terminal here, I have an NGINX Plus instance. This is, in fact, my own demo environment, so I'm probably lagging a little bit in versions, if I'm being honest. Oh, well, I'm only lagging a patch level. I'm on R25. The current NGINX release is R25P1, so I'm fairly new. That being said, supporting TLS and SSL is hardly a new feature in NGINX, so I could have been many versions behind and still showing you everything about the demo today. Ultimately, I am looking to communicate with a backend. So if I have a look here, I have a configuration file in my, as we talked about, the conf.d directory called, I've simply called it nginx.beaton.io.conf. I have a preference to use the actual host component, the domain name, dot as a naming format for my configuration files in conf.d. Your mileage may vary, whatever suits your operational procedures, but that's how I do it. If you have a look inside of that file, I have configured it up with everything, well, almost everything we need today, but first and foremost, I have configured up a server here that's listening on port 80. All of these ones with hash marks are comments, so this entire part of the configuration is not utilized at the moment. So what we're looking at here is very simply a virtual server that's specifically hoping to match the host name of nginx.beaton.io. It's listening on port 80, and we have a simple catch-all prefix location match of /, within which I'm doing two things. I'm setting a header for the upstreamed proxied request, where I'm setting the host header to match $host. I'll explain that just after I've explained the second statement here. It makes more sense then. The second part here is a proxy pass. So essentially, I'm telling the NGINX server that once I get a request that matches this location, I'm going to proxy pass that request to somewhere. And in this particular case, I'm going to proxy pass it to http:/my backend. My backend happens to be a host name that I have in, well, let's call it DNS resolution in this network. And it'll correspond to an internal IP address, 192.168.something or 10.something.something, etc., etc. So I'm proxy passing on the internal network to another instance altogether. But let's remember that name, my backend. So why did I do this business then? Proxy set header host equals $host. Well, first, let's understand what's $host. $host is a variable within NGINX that gets populated when a request comes in. $host gets populated with the value of the host header of the inbound request. So in other words, if I have requested http:// the $host part would contain nginx.beaton.io. And I want to make sure that the backend that I'm proxying this request to sees the same host header. So therefore, I'm doing this. If I did not include this statement, the upstream server to which I am proxying this request would see a host header of my backend. which might break the backend application. So it's kind of important to recognize. The second part here, the TLS configuration, we'll get back to momentarily. Right now, I'm just going to make sure that the configuration we're looking at is in fact the one that's running. So I'm going to do a quick reload because I can't remember if I remember to do so 5 minutes before you guys arrived at the meeting. So we're going to do our reload. Okay, that's fine, and so on. We have now, in fact, reloaded. Now, remember this name, my backend. Now, I am on the NGINX server here, as we indicated by the fact that we can verify the version running and so on and so forth. This name obviously needs to be resolvable on this NGINX server for the communication to work. As a matter of fact, when I reloaded the configuration, NGINX did a sanity check of the configuration. It saw a quote unquote variable name here that it didn't recognize internally. So it did a resolution check automatically as part of the configuration reload. If it hadn't been able to resolve this name, it wouldn't have allowed me to reload the configuration. As a matter of fact, that's pretty easy to illustrate. Let's do a quick little, perhaps I should, no, let's use now, it's fine. Let's do this, which is a non-resolvable name on my system. So yeah, sure. And if I now do reload, it'll tell me it can't find it, so it won't reload the configuration for me at all. NGINX is very, very, very practical from that perspective. It kind of saves you from yourself in certain scenarios. Anyways, I'm going to do a reload just to be on the safe side. So we're all good now. Well, then, now that we are all good and these things, what happens then if I pop on over to a web browser? And let's say I go here and I say nginx.beaton.io. It would default to HTTP, but let's make it explicit and actually include the protocol ourselves. So I'm now going HTTP, which is port 80 by default, unencrypted, to nginx.beaton.io. This is, of course, not recommended. The entire internet has essentially agreed upon the fact that all communication should be encrypted at this day and age, which is great. But anyways, going to this, yay, I had actually done things correctly. I am so proud of myself. So I'm now seeing a welcome to NGINX page here. So that, of course, is the standard page that NGINX comes with, which means that it's found in, well, 440 million and growing number of servers out there. So let's make sure that we actually know where we're at. So I'm going to pop back over to my terminal real quick. Then I am going to go over to my actual backend container. If I curl localhost here, I should be seeing, yeah, that's essentially the page that I'm seeing. Let me go ahead and change that page a little. So that's the page. I'm going to go ahead and say, welcome to NGINX. Like so, and perhaps there. Now, this is not a configuration file. This is just a backend static file, so I don't even need to bother myself with reloading configs or anything of that nature. But if I pop back over to the web browser now and I do a reload, let's just verify and make sure that we are in fact seeing a new page. There we go. So we know that we are indeed dealing with the actual page in question. Perfect. But what's not so perfect is this big not secure sign here. The reality is, during our demo, we're not going to get completely rid of the not secure bit because we're going to use a self-signed certificate, but I'll explain what the difference is and why it's there and so on and so forth. So first, let's talk about how we generate a certificate. In our case, we're going to use a so-called self-signed certificate, and that means in turn using an internal command line tool for that, namely OpenSSL. So I'm going to copy a command into my terminal, and then I'm going to explain each and every level of what that command does. The command in question looks like, where are we now? We're in the right place, are we? Here we are. And yes, so I should be able to, sorry, should be able to do that and paste the command. So the command looks like this. I'm going to sudo because I'm not an admin user on this box. The command is OpenSSL first and foremost. OpenSSL is a massive tool set that performs a number of different functions when it comes to encryption. But in this particular case, we're specifically going to make a request. The request is for a certificate, and we're giving it a parameter of X509. It modifies the request subcommand by telling OpenSSL that what we want to do here is to make a self-signed certificate instead of actually generating a certificate request, which can subsequently be provided to a CA, which would normally happen. We have the nodes, which tells OpenSSL to skip the option to secure our certificate with a passphrase. Normally, you'd provide a password for a certificate as well. We're not interested in that. Dash days 365, pretty self-explanatory. This certificate will have a validity of 1 year. New key RSA 2048, judging by the conversations we've had so far today, also pretty self-explanatory. Essentially, we want to create a new certificate and a new key at the same time. And the RSA 2048 bit tells us to make an RSA key that's 2048 bits long, fairly secure. Key out tells us where we want to store the resulting key, and out tells us where to store the resulting certificate. So not very complicated, but once we do this, we're going to be presented with a number of questions. The majority of these, since it's a self-signed certificate, you can skip. I'm OCD enough to, oh dear, yes, of course I am indeed, as I didn't see, I am indeed admin here, so and I'm also on the wrong box, which is excellent. So let's just do that. In fact, going to be here. So that explains why sudo wasn't there. We should have looked at the $sign here to establish the fact that we're not an admin user. Anyways, it's the same command that I pasted in. We've gone through all of the elements. I'm going to go ahead and run the command, and I'm going to get a lot of questions. You can skip most of these. I'm OCD enough to not do so, but there is one specific one that you cannot skip, and I'm getting to that momentarily. Organization name, company name. And it's this one, the common name. You'd really need to at least fill this field to make sure that the certificate can match the host name of the requests that you're going to be securing with it. In my case, it's going to be NGINX.io, like so, and ultimately I'm going to give it my email address at f5.com, like so. And the certificate and the key has been generated. If I want to have a quick look at it, the key would look like this. Let me just copy that string before I press enter. So the key would look like this. And for that, I would need sudo. And the search will look like this. So pretty simple stuff. It's a PEM format standard. You would have seen this 100,000 times before. Now, all I've done so far is to create a certificate, the self-signed certificate and the key. That does not help me to encrypt the communication. I still need to do the configuration bit, as we remember from the presentation. So in the configuration bit, I've done a lot of the heavy lifting already, so I don't have to sit here and type configuration in front of you. One of the things I've done is, first and foremost, I am now in the NGINX folder, the default install folder for NGINX. So in that, I would have a number of files and folders. These are all default files and folders, with the exception of the folder snippets that I've created here. That one is of my creation. The rest of it exists with a default installation. What do I have in the snippets folder then? I have two files. I have a self-signed file .conf and an SSL params.conf. What's in these then? In the self-signed one, I simply have the reference to the certificate and the key. So rather than hard coding that into the NGINX configuration file of my choice, I can include this file wherever I want. What's the benefit of that? Well, it means I can include this file wherever these two certificates is needed. In our example here, that's not super relevant, but imagine the scenario where you have a wildcard certificate for a number of different domains that has a number of different configuration files and so on and so forth. Writing the same instructions time and time again not only is dull and boring, but it also increases the risk of an error here and there. So it would be a better approach to just separate out those statements into another file and include that, which is what we're going to be doing here. We also have exactly the same relationship in the SSL params file. Rather than writing this out in each and every place that needs encryption, I'll specify it in its own file, and I'll include it using an include statement. Now here's the URL, and I can throw that out over chat just for good measure. Where are we? There's the chat. So this URL that I'm going to show you on screen in 2 seconds is worth carrying with you in your back pocket, because it'll help you on a number of things when it comes to configuring up different software. What's kind of cool is I gave it the base URL. I didn't give it any cookie, any query string, anything at all. And it automatically defaults to NGINX. I absolutely love this. But of course, they have the backing of percentages here. You can choose configuration statuses, old, which I would recommend stay far away from. So essentially you have intermediate and modern. We're looking at some other bits about the environment as well. And it provides you with a sample configuration with every bit, which is kind of cool. It's also using the DH param here, which we're going to talk briefly about. We're not going to cover that because it takes too long. It's absolutely recommended to use Diffie-Hellman parameters to increase the cipher strength from 2048 to 4096, for instance. And it's also imperative for perfect forward secrecy. But creating the Diffie-Hellman parameters, even on a fast computer, that would take many minutes, and just looking at that isn't really relevant for us. Anyways, so looking at the configuration here with intermediate, you'll see we have the 1.2 and 1.3 protocol specified. We have a number of ciphers and strings and whatnot. If we go to modern, boom, it'll remove most of that because now we're limiting ourselves to TLS 1.3. So essentially, this is all you have to do to ensure TLS 1.3 communication. It'll save you a lot of time hand coding this and also avoiding errors. So it's a handy URL to have up your pocket. Although, with all that said and done, let's trickle back to the workshop. So I'm going to pop back over to my terminal. We've verified that I had the two include files, the self-signed, which includes a reference to the certain key, and the SSL params, which includes a reference to these parameters. So let's go ahead and alter the configuration then to suit our needs. And it's conf.e nginx.conf. All I have to do essentially, first and foremost, is I'm going to uncomment these lines. So let me just, I'm OCD enough to take that extra space away as well. And this actually should be commented. So let's do that there. Boom. So what are we doing here? I'm listening on 443. I'm defining that it is encrypted. I'm also adding support for HTTP2, and I'm telling it to be the default server. If other requests coming in on well, if any request coming in on 443 that doesn't match any other virtual server will default its way into here. I'm making the same statement, and this is an IPv4 version of the statement. I'm making the same IPv6 statement. Doesn't matter, my server doesn't talk that way, but it's there for you. And I'm including the two snippets. Actually, let me, I'm a big spender, so I'm going to afford an extra line break there. I'm including the two snippets. The snippet self-signed, which is the reference to the certificates, and I'm including the SSL parameters as well, allowing me to specify how I want to communicate with the server. Other than that, the location, as you see, is perfectly identical between port 80 and port 443. No change whatsoever. So let's go ahead and just save this configuration. And since I'm a good boy, I know that I need to reload the configuration as well after I've made a change. I'm just getting a warning that the SSL stapling is ignored, and the reason for that is this is a self-signed certificate. I can't validate the issuer of the certificate, so we don't need to worry about that. It's just a warning, not a failure. Now we can pop along and we can go over to our web browser, and I can go to https://NGINX. And now I get a warning. This is good news. This is exactly what we wanted to see happen. We get the warning because the certificate is self-signed. You see, the error I'm getting is that the certificate authority is invalid. But that's great. It means it's working. It means that the certificate and the key exchange has happened or is happening now. But in order to actually communicate using a self-signed certificate, I have to jump through some hoops. I have to click that button and I have to say continue, even though it's considered quote unquote unsafe. And there we go. I am now, as I mentioned earlier, we're not going to get rid of that not secure moniker, but when we click it, we're going to see that we are in fact seeing a certificate here, but we're not considered secure because it's a self-signed certificate. With that in mind, I mean, obviously for a business, for an enterprise, all of that, they would use, more than likely, they would use one of the predominant certificate authorities out there to generate any and all certificates. But even for hobby use or small businesses, there are options out there. NGINX is actually one of the sponsors for ACME, or Let's Encrypt, as it's called, which issues proper, trusted public certificates for free. So they have short validity, they're only valid for 3 months, but you can automatically renew them. And there is in fact a certbot. So Let's Encrypt is, they have a piece of software called a certbot that you can run on a Linux server that will automatically renew those certificates upon request, and it'll automatically configure your web server or proxy server to use the updated certificates and so on and so forth. And certbot does indeed support NGINX. All you have to do is add the -- NGINX flag in your certbot command and you're off to the races, which is quite cool. But the final thing I want to take you guys through in terms of showing you how we can go about this thing is the one thing we have already done. If I switch back to my terminal, one thing we've already done, if you remember in the snippets.ssl params, is we've already added a header telling the client strict transport security should be always. This means we should always use HTTPS for this communication. Remember, in NGINX world, add header will add a header for the response to the client. Inversely, in the configuration that we're going to mildly alter now, conf.de/NGINX. Inversely, proxy set header will create or manipulate a header going to the upstream. So you have proxy set header going to the upstream, you have add header going to the client. Distinction to remember. Now, we don't want to allow for port 80 communication anymore. That's not our style, not our speed. We want to get rid of that. So what I want to do there is I'm still going to listen on port 80. I need to have something picking up the phone if a request comes in to port 80. But rather than providing content, I'm simply going to return, and I can choose either a temporary or a permanent redirection. Doesn't matter for the intents and purposes of the example. What I meant by that is I can choose between 301 or 302. It doesn't matter. It both will work. But I'm going to return where I want people to go. And luckily, I don't have to type this out manually because I can rely on the same variables. Where am I now? What did I press? Did I press? And where's my? Oh, there we go. There we go. Sorry, I had pressed a button and I didn't know which. I can use the variables that we were talking about earlier. So I can use the host here, but I also need to include the request URI. So whatever comes after the host component needs to be passed along with in the return statement as well. So we're ensuring that we're actually getting to the right place. And as a matter of fact, let's just get rid of these lines. They are doing nothing but annoy us at this stage. By this configuration, if I save that and I go ahead and I'm a good boy, I'm going to reload the configuration as well and get the same warning, but it's still fine. I pop back over to my web browser, and this time I am going to ensure that I am indeed going to HTTP port 80, in other words, and my URL. And what happens is I automatically and magically get transported to HTTPS. No interaction on the user required. This is just a communication between the browser and the server. What happened here is the browser sent a request to my NGINX server on port 80 asking for content. The my NGINX server in turn says, nobody, we do not serve content on port 80. Here, have yourself a nice and pretty HTTP 301 telling you to ask me again, but this time use HTTPS, please. The browser received that response, and instead of interacting with me, the user, it just decided, you know what, this server is kind enough to tell me what I need to do. I'm just going to go ahead and do that. I'm going to reissue this request, this time using HTTPS as it informed me to do. And that, ladies and gentlemen, elegantly takes us to the end of it. Essentially, what we've done, the last step we did now is exactly this. We did the redirect. We've kind of done elements of this SSL security key exchange parameters. That was in the SSL include file that we talked about. Essentially, it limits the parameters that the list of parameters you can do. And now you can increase the size to 4096 using a parameters group, a Diffie-Hellman parameters group. But the calculation of that using, again, OpenSSL, specifying DH param, Diffie-Hellman parameters, you can create a new file called this, right? The reason I didn't want to take it into the word demo part of it is once you start this command, it can take anywhere from 4 to 20 minutes to run, depending on the speed of the computer. It's a heavy computational task it runs through to create those parameters. But it is possible, and it's also necessary if you want to include perfect forward privacy. Simple statement to add it in the config, SSL DH param, and include the file. This one we already had in our configuration. We did add that header to the client to enforce that any future request, it should automatically and always ask for HTTPS. It should never bother us with an HTTP request ever again. Yeah, so we can set cache timeouts and cache sizes for our local disk cache for the SSL session states. Now, finally, closing words on the last minute. We obviously have additional security products outside of just encrypting traffic. Briefly, we're talking about, of course, NGINX Plus with AppProtect, which is a dynamic module for NGINX Plus, essentially building upon the advanced web application firewall capabilities of F5's BIG-IP. We have that in two flavors, the standard, and we have it in a DDoS or DOS flavor as well, providing a range of DOS attack protection as well, including slow LoRa, slow HTTP. We have one of the most popular ingress controllers for Kubernetes out there, and when it's based on NGINX Plus, you can add things like OpenID connector auth to authorization and identification, as well as, for that matter, include NGINX App Protect in either flavor directly into the ingress controller. I'm going to leave you with some resources on screen, some links on screen. And as Anya said, the presentation will be recorded. The slides will be made available. With this, thank you so much for your time. And Anya, I'm handing it back to you.
Thank you, Leif, for that great presentation and the fantastic demo. I know we're at the top of the hour. We might take a minute or two, Leif, just to go through some questions if people want to hang on.
I'm fine with that.
If you're okay with that.
I'm fine with that. So that's answered, that's answered, that's answered. Is there any change when talking HTTP and TLS 1.3? Well, HTTP 3 isn't quite formalized yet. Well, it kind of is, but it's not really there. We do have support for HTTP 3. Of course, there are some elements changing in terms of binary communication versus ASCII and all of that, but essentially from the 10,000 foot perspective, which we have been talking about here today, it isn't massively changed. It's a more modern approach. It's a more secure approach by virtue of that, but principally they're similar. This is what more about install. The requirement is to install NGINX under the app. I'm just looking at Faisal's question here. The app range. Start. So he's looking for from an operating system security perspective. Can we install NGINX in position X and run it under a specific user context and so on and so forth? Yes, it's absolutely possible. As a matter of fact, the very first line in the base NGINX configuration file is to establish what user context should this process run as. It can absolutely run as a non-privileged user, and you can even there are some hoops you have to jump through, but you can even deploy the system as a non-privileged user. The only caveat to what I just said is you can obviously not define listeners for non-standard ports as a non-privileged user. That's simply not doable in Linux. So yeah. Anyways, let's see. Following that, can I install the SSL search, etc.? Well, that's Faisal following up. I'm guessing that what it means here is can a non-privileged user install the SSL search, etc.? Assuming that you provide access to that specific function under OpenSSL to a non-privileged user, then I would say yes, because you can afford the opportunity to reload configuration of NGINX to a non-privileged user if you should so choose. How do we automate certificate generation with Let's Encrypt? That can be used by NGINX by utilizing Let's Encrypt's certbot. The certbot software does support NGINX, and it'll actually generate the configuration for utilizing the certificates for you as well. I'd recommend doing some manual cleanup of that, but it will generate a perfectly serviceable configuration for you. What is configuration required to make NGINX proxy to HTTPS backend? Well, that depends. I mean, you can do MTLS, mutual TLS, having a client certificate on the front end and a server certificate on the back end, and establishing MTLS between them. But the simplest format is just when you proxy to the backend, proxy to HTTPS. You don't have to do anything more than that, realistically speaking, because in that sense, the front-end proxy will just act as any normal client towards the backend, and the negotiation of encryption standards will then take place between the front-end and the backend, as if the front-end NGINX was Google Chrome or whatever. It's not the way I would do it in production, but it's perfectly valid. doable. How can we deal with SSH configuration? Well, SSH configuration would be dealt with in the stream context in the basic NGINX configuration, because SSH is OC model layer 4 rather than OC model layer 7, which is HTTP. So can we endpoint and or proxy SSH? Yeah, of course, absolutely. We do that in the TCP/UDP segment, which is the stream context. Miloslav says, I think TLS 1.3 is not recommended or not. Well, it is and it isn't. It's strongly recommended if you want to have the absolute pinnacle of security as it stands right now. The only drawback is, as I alluded to earlier in the presentation, security when it comes to our industry has always been a pull and tug match between absolute security and absolute usability. You're going to have to compromise on one side or the other. Either you're going to make something more difficult to use but more secure, or you're going to make it easier to use but less secure. So somewhere in the middle there is where you're going to find yourself existing, and exactly how close you're going to be to more secure and less usable, or more usable and less secure, depends on the nature of your business. For instance, an online banking service would probably lean towards the more secure and less usable than something like the login to post a movie review on IMDb or something like that. I'm just pulling examples out of my thin air here, but anyways. So slides and reference that there. Do you suggest to use Let's Encrypt in production environment? Well, I wouldn't suggest that you use certificate authority A over B or B over C or anything of that nature. But if the question is, would I trust a Let's Encrypt certificate in production environment, is from the base perspective, yes, I would. I would do additional research if I was essentially trying to encrypt the front door to the Fort Knox. But here's the thing. That's not because Let's Encrypt is Let's Encrypt. That's not because Let's Encrypt is free. That's because if I'm doing something that has significant enough security requirements, you better believe I am going to research any certificate authority that I'm going to put in place, be that Let's Encrypt or any other out there. Do I trust Let's Encrypt? Yeah, to a certain, well, to more or less the same degree as any other. Yes, I would trust them at face value. But again, the more secure I want to be, the more research I would put into the elements that I put into place. Was that all of them? Slides?
Yes, that's amazing. There was a couple more that were in the chat, but I think you had actually answered a lot of them as you went through your presentation. So
excellent.
To that end, and 7 minutes over our end time, I would like to thank you, Leif, for the fantastic presentation again, the demo and the marathon of questions that you've just went through. I'd like to thank all of our attendees for joining today. We hope you found today's session beneficial. As previously mentioned, we will be sharing Leif's slides and the recording with you via email after this. But please keep an eye out on nginx.com for all of our upcoming webinars and events. And we hope to see you all on our next webinars coming up again soon. So to that end, thank you all, and we will talk to you soon.
Cheers.